Assalamualaikum. Today we'll be focusing on three process steps. First, hazard recognition, assessment, and control in natural product laboratory. But hold on, we need to understand the three terms. First, hazard. Hazard is something that can cause harm, potential source of harm. Second is risk. Risk is more to the probability of getting harm and how severe it is. Third is control measure. It is more to actions implemented to eliminate that hazard or reduce it to an acceptable level. So I will be explaining about the soft lid apparatus. Now, why is it considered as hazard? First step, recognize the hazard. So the soft lid apparatus is a fragile, complex glassware that requires continuous heating of highly flammable solvent. For instance, like DCM, dichloromethane, ethanol, and hexane. So why is it considered as a hazard? Now let's take a look at the first point, solvent hazard. So the solvent that we use are heated to its boiling point for hours. And let's say if there is any leakage or crack at the glassware, this will allow the vapor form of that solvent to escape. And when that vapor is in contact with the heating source, then ignition will occur. Second point is the toxicity. So if we inhale too much of that solvent, it can cause harm. For instance, if we use DCM as our solvent and we inhale too much of it, then it can cause carcinogenic effect. For the third point, the pressure build-up hazard. So we all know for a fact that when the solvent is being heated, it will vaporize and travel to the condenser. So what if that vapor does not even go to the condenser? So there will be an accumulation of vapor. Then the vapor generated has nowhere to go and it will create pressure inside that fragile glassware. Hence, this can cause explosion and release of hot flammable liquid. Move on to the risk assessment. So we could see that the probability of that incident to occur, I will give a rating of 3, which is conceivable. So we all know the soft lid apparatus will be running for hours. So the longer the operation, the higher the chance of condenser water flow to stop, and this could cause leakage of vapor. As for the severity, I will give a rating of 5, catastrophic, because when there's ignition of solvent vapor or glassware explosion, that it can cause severe burns or even major fire. Combining together the probability and the severity, we will get the value of 15, which is considered high. For me, it is logic because the soft lid apparatus will be running for a long period of time. And then we will also use a highly flammable solvent. Not to mention that apparatus is also very fragile. So I guess it is one of the And for the last step, it is the control measures. Here, we are referring to an upside down pyramid and we will start from elimination first. So under this category, if there's a safer and alternative method like microwave assisted extraction, then it is better to use that rather than soft lid apparatus. So if we could not eliminate, then we'll move further down the pyramid, which is the substitution. We can substitute the highly flammable solvent with a less flammable solvent. And moving down the pyramid, we have the engineering controls. So here we can perform the entire setup of the soft lid apparatus inside a fume hood with a suitable sash height. And then also we can install a condenser flow monitor with an alarm to alert if the cooling water stops. Next, we move on to the administrative controls. Here we can develop SOP for the assemble, the monitoring, and the dismantling of that apparatus. We can also check and record condenser, water flow, and heating temperature for every hour. And lastly, we should never leave a running soft lid system completely unattended. Last but not least, it is the PPE. So the operator could wear a fire resistance lab coat, and also that person could wear safety goggles or face shield at all times.
We're going to talk about the non-halogenated organic waste by step, which the first one is to recognize the hazard, and then the assisting and also the last one is the control measure. So firstly, we need to recognize the hazards. What is the hazard? So in this case, it is the non-halogenated organic waste containing used to collect the leftover solvents and rinsing waste in the natural products lab. For example, we have acetone, ethanol, methanol, etc. So why is it a hazard? So it is highly flammable, vapor accumulation. It is also pressure built up in the container, where if the cap is closed tightly, the vapor expansion will cause the swell of bottle, and then it suddenly puff, release when open. And lastly, it is compatibility of mixed waste. Jump into the second step, which is assess the risk, where the activity here is pouring non-halogenated solvent waste into the designated waste container. So this is the risk assessment table of non-halogenated organic waste. So in here we have the probability of incident, which is 4. It is possible. Where the waste is poured frequently, spill may occur if a funnel is not used, and also vapor can escape easily during the pouring. Next is the severe. The rating is also 4, which is it is major, where the flammable vapors may ignite, which can cause burns, flash, fires, and or a laboratory fire. So for the risk score, the probability times the severe, we got 16, which is high. This is because the combination of high flammability, vapor formation, and the presence of nearby ignition sources such as hot or electrical. So for the last one is the control measure. We're going to start with the elimination, which is the first one. So use the smallest amount of solvent needed or evaporate leftover solvents fully before throwing them away. Next, for the substitution, can use ethanol instead of diethyl ether because ethanol is less flammable, so making the waste continue safer. Next, replace acetone rinses with 80 to 95% ethanol because ethanol it will produce fewer vapors and lowers the fire risk during handling and waste collection. For the administrative controls, label the bottles of the waste clearly, which is non-halogenated organic waste, flammable. and then check the waste levels daily. So we need to make sure that it does not fill the parts of 80%. And then follow SOP, use a funnel, and also clean spills immediately. And lastly, for the PPE, wear solvent-resistant natural gloves, wear a lab coat which is flame-resistant pre-fit, and lastly, wear safety goggles at all
So
times.
let's talk about the bumping of rotovap. So let's talk about what is bumping. Bumping actually is a chemical hazard where the solvent does not boil smoothly, instead it being superheat and then it release heat energy in a rapid explosive burst of vapor. So just think of it like a mini explosion in a flask. Okay. So why it is a hazard? There are two main reasons. The first one is acute exposure. Why I say this? This is because the expelled solution create a mist or concentrated cloud vapor and it will increasing the risk of inhaling harmful solvent to our lung. Okay, so for the second one, it will create vapor path to ignition sources. So as we know that flammable vapors escape the sealed system of the rotovap, and then many standard vacuum pump have electrical component that can spark. And if this spark can contact with the high concentration of flammable vapors, it will create an immediate fire risk. So we have seen that this bumping actually will escalate a dangerous situation. Now that we recognize the hazard, so let's assess the risk. Based on a probability of incident, we have rate it as 4 possible because of the bumping is a frequent operational risk that has a potential chance to be occur. And then regarding the severity, we have given it as 3 serious as the chemical exposure from the hot and concentrated solution will splashing it out, and this will lead to health effect such as chronic effect and exposure to a very toxic chemical. And then when we calculate the risk score, we will get the 12 as a medium risk, and this medium risk score for chemical hazard actually will demand a high priority control even though this score is not high. Finally, let's look at the control measure, and starting from the elimination, the bumping can possibly be eliminated by applying strict standard operating procedure. And moving to the substitution, we actually can substitute a highly volatile solvent to a less volatile solvent if the chemical reaction allow. And then under the engineering control, we should ensure a bump trap of the rotovap is clean in order to prevent ejected solution from contaminate the condenser. And then moving to the administrative control, we need implement a mandatory training on vacuum application gradually to reduce the probability of the incident, and we should apply a strict limit volume of the flask to prohibit the overfilling of the solution. And the last one is PPE. We should wear a chemical splash goggle to protect our eye, and then wear a fire retardant lab coat as our last line defense.
Continue with stirring hot plate, where here we will recognize the hazard, assess the risk, and apply the control measures. Stirring hot plate is a device that combines hot plate for heating and magnetic stirrer to make solution. This device is very useful in lab, but also comes with several hazards. First, high temperature and thermal burns. Hot plate can reach a very high temperature, about 500 degrees Celsius, and it stays hot even after being switched off. So if a person accidentally touched the plate or hot glassware, this can cause serious burns. Second, fire and ignition hazard. So all hot plates can create sparks that may start fire. And when we heat flammable liquids, the vapor can ignite, especially if the temperature is set too high, and accidental turning on the wrong setting, like the solution only needs stirring, but instead the person set it to heating. So this may cause overheating or fire. The third one, electrical shock. Stirring hot plate use electricity. So like damaged wires, loose plugs, how hot touching the hot plate or spills around the unit can lead to short circuits. Electric shocks for experiment we focus on chemical splash due to boiling or vigorous stirring. The probability of incident is rated 3, conceivable. So the explanation, if we increase the stir speed too fast or heat liquid close to its boiling point, bumping or splashing of hot solution can happen. The severity is also rated as 3, which is serious non-fatal injury. Splash of hot solution to the eyes or face can cause serious burns or eye damage and may need for urgent medical treatment. So the risk score is 3 times 3 equals 9, medium. The combination of hot liquid and mechanical stirring gives a conceivable likelihood and serious consequences which produce medium risk. To reduce the risk, we apply the hierarchy of control. Firstly, we have illumination. We should avoid heating flammable solvents directly on hot plates when there are safer alternative methods like water bath or steam bath that can be used. Under illumination, we have substitution. Highly flammable solvents can be replaced with less volatile ones, and use hot plates with safety features such as built-in temperature feedback systems. Third one, engineering controls. Hot plates should be placed on stable, heat-resistant surface with proper ventilation, and heat-resistant glassware such as borosilicate can be used and inspect for any crack. The fourth one, administrative controls. SOP for hot plate use should be implemented, and routine inspection for any hot plate damage should be maintained, and heat reaction should not be left unattended. The last one, PPE. Person handling stirring hot plate should wear lab coat with sleeves fully extended to the wrist, safety goggles, heat-resistant gloves, and gloves to shoes.
In conclusion, the Natural Products Laboratory is filled with diverse chemical processes which are extraction, filtration, solvent handling, each bringing its own set of hazards. Through this presentation, we all explore how effective safety management begins with understanding of recognizing the hazard, assessing their risk, and also controlling them using proven strategies. So in the end, the chemical safety is not just a requirement, it is a mindset, where a safe laboratory is built through consistent awareness, proper procedure, responsible teamwork. When we identify the risk earlier and choose the right controls, we protect not only ourselves, but also our environment, our research, and our future works. Thank you.